Hi everyone, Dr. Madi here, and in this class activity, you will become familiar with the PincherX 100 robot arm from Robotics and the Vision Kit. You will also be able to identify the robot's links, joints, actuators, and sensors. Just a reminder that the lessons in this series is gathered in a playlist, and you can access the text in the course's GitHub wiki. For most of the projects in this class, we will use the serial robot arm, the PincherX 100 from Robotics with the Vision Kit for vision-based control. This robot arm is controlled by Robot Operating System, or ROS2, and we will use ROS2 Humble, which is the 8th release of ROS, and it is a long-term support LTS release, meaning that it will be updated and the bugs will be fixed until May 2027. We will use RViz as the visualization tool to visualize the state of the robot, including its position, orientation, and sensor data. Python is the preferred language, and we will use the Python ROS API, which sits above ROS, so that even if you are not proficient with ROS, you can still control and program the robot arm. The robot should be fastened to an 18-inch by 24-inch wooden board for stability during operation. Here are the steps to do. Unbox the robot arm and the Vision Kit. The robot arm comes pre-installed, and all you have to do is attach the gripper. Note that you can always 3D print your own gripper for the specific needs of a task. Follow the instructions in this video to do so. Make sure to take into account the joint limits when turning the robot arm, because if you turn it beyond the joint limits, you will damage it. Take this into account when programming the robot as well. The joint limits for the PincherX 100 robot arm to ensure a safe range of operation are as this table. Now assemble the Vision Kit according to the box instructions, which are straightforward. The only place that you may need help is installing the April tag, which is a visual fiducial artificial feature system. Targets can be created from an ordinary printer, while the April tag detection software calculates accurate 3D position, orientation, and identity of the tags in relation to the camera. Follow the instructions in this video to install the April tag. Make sure that the orientation of the tag is like the video. The template for the whole layout is shown here, and you can download it from the course's wiki as well. Then use a set of M4 PEM nuts and thumb screws, or 3/4 inch number 8 rounded panhead wood screws to fasten the robot arm to the wooden board. Now it's time to power on the robot and connect it to the computer. Warning: while the robot is powered on, exercise caution to avoid touching any cables, connectors, boards, or other electrical components on board, as this could lead to the risk of electrical shock injury. First, power on the robot, and then connect one end of the micro USB cable to the computer and the other end to the U2D2 controller. Our arm is now ready for ROS installation in the next class activity. Based on what we have learned in Lesson 1 in terms of the kinematics design, what kind of robot is the PincherX 100? Got your answer? Drop it in the comments. I'll reveal later whether there's a right answer or not. Now identify the robot's links and joints. After you got the answer, comment that and I will give you confirmation. The links of the PincherX 100 robot arm are actuated using the Dynamixel X series smart servos by Robotics, where each smart servo has a motor, a control board, a gearbox, and an encoder that can fine-tune smooth joint motions. These servos come with a small-sized USB communication converter that converts USB that the computer understands to serial communication, TTL or RS485, that servos understand, enabling controlling and operating the servos with the computer. It has both 3-pin connectors for TTL communication and 4-pin connectors for RS485 communication, which are two different methods used for data transmission in electronic systems. What is the communication used in the PincherX 100? Note that the type of communication is dependent on the servo model used, but you can see that from the connected pins. Comment and check with me and others. Now let's talk about the sensors. As mentioned earlier, the smart servos have embedded encoders that provide feedback on the position, velocity, and torque of the motor. This feedback is used to control the motor and to ensure that it operates within its safe operating limits. According to Lesson 1, what kind of sensor is this encoder? Again, comment and get the right answer. The other sensor that we will use in this course is the camera and the vision kit that comes with it. This sensor will allow us to add a computer vision component to our robot setup to perform different tasks that need that extra eye. The camera that we will use is the Intel D415 RealSense depth camera, which features 1920 by 1080 resolution at 30 frames per second, with a 65 degrees by 40 degrees field of view and an ideal range of 0.5 meters to 3 meters. According to Lesson 1, what kind of sensor is this camera? According to Lesson 1, what is the main limitation of a single camera, and how do you think this camera solves it?